This is another notebook that we'll be going through today for the optimal extraction from a 2D spectrum, in this case for simulated data from MIRI LRS. Of course, this can be utilized for other 2D spectra, and I want to make it very clear that the techniques here are not the final techniques recommended from the instrument team. They are simply using a number of tools that we have developed that can be used as a baseline and foundation for optimal extraction. But for your particular needs, you may want to refine your technique. Hopefully the various instrument teams will provide recommended techniques in the upcoming months. For now, we're going to go through this notebook and somewhat quickly, and we can spend more time on it during the actual webinar. Okay, so the first thing that we want to do is, start at the top. Start over, I'm sorry about that. And we're going to want to import our packages and define some functions. These are just basic functions that we're using to define various weights on the image. Then we want to download our data files. You can see here when the star is running that the cell is still running. That's because we're downloading data. The subsequent cells will run after the previous cells are finished running. Then we can define all of our various file names. We can read in the files using the JWST data models package. And we can print various information about the data. So let's let all of those continue running. They should just take about a second more. Let's see. Should be one more second. Taking a little longer than I remember. All right, done running, and here we go. That's the information, and we just want to show this now. There's your 2D spectrum. We can do a cutout and transpose it, and then we can open it in one of the instances of JDAViz, which we call SpecViz 2D. SpecViz 2D shows your 2D spectrum at your top and your extracted spectrum at the bottom. The default is a collapse in your position space, but if you want to do an optimized extraction using the AstroPi SpecReduce package, you can open up the spectral extraction tool, plug in from our plugin toolbar, and this allows you to define a number of different variables, including your trace type, which is flat. It's on pixel 30. You can export that. You choose your background next. It can be one-sided or two-sided. You can control things like the separation and the width. And you can, of course, export those backgrounds. And then you go down in here and you want to do your extraction. And that, in our case, is we only have one 2D image here, but if you did other manipulations, you could potentially have other data products. And then you can have your boxcar or optimal horn extraction, and your extraction width. You can see how changing that, right, changes what your extracted spectrum is going to look like. But if we put it right there, we can extract it. Let's just say that's it. And we're going to call this our target. And we are going to extract it. Okay. Now, you see that it pops up here, and we have our collapsed spectrum as B. Now, what you might notice is that you are in pixel space. This is due to a technical limitation that we have at the current time, but that is going to be fixed in the relatively near future. For now, there's another very easy fix where we simply are able to extract that spectrum from our SpecViz 2D. And there's our spectrum, okay, that we extracted. We still do need the wavelength axis, so what we're going to do is we're going to read our S2D file into a Spectrum 1D object. Spectrum 1D is the class for any type of spectra. It was historically named the Spectrum 1D because those were the only 1Ds at the time, types of spectra at the time, and they are now inherent to the SpecUtils AstroPi package. But it's too late to change the name, but we can keep a Spectrum 1D object and use it across so many different AstroPi functionalities. In this case, we're going to get the axis, the x-axis, and we're going to create a new Spectrum 1D from both the x-axis and the flux in SpecViz 2D. And we are going to create that spectrum and plot it up. And now you see we have a nice calibrated spectrum in wavelength space. And we can open up our plugin toolbar and do all sorts of analysis. So what we're going to do is we're going to call that our jpipe x1d file. Okay, that's going to be how we name it. And we're going to read that from, okay, so we have that extraction. And now we're going to, and just to remind you, that's called target spectrum. Okay. Now we are going to read a Spectrum 1D from our file, okay? And we are able to show what that looks like in SpecViz, okay? And of course, that looks pretty good. And you can see that it's wavelength calibrated. We read that in as a Spectrum 1D. And we can move on and do also an extraction from the 2D image, okay? And we define our center, our background width, separation, all that good stuff. And we're able to confirm that this is our extraction window that we want. Here's what it looks like centered. Here are the background regions. And we are able to use AstroPi SpecReduce package, which is the foundation for the SpecViz 2D extraction as well. But in this case, we're doing it from the API. And we're able to define our trace, we're able to define our background, and we're able to show what that looks like. Okay, there we go. Here's our trace, here's our background, and here's our 2D spectrum minus the background. There is just a note that when you use the median to do different combinations, okay, using statistic median, you actually can't support partial pixels. So that's just illustrating that point there. There's also things like doing advanced traces, where you, instead of just doing a straight line, you're able to try to optimize that based on the centroiding of Gaussian. And then you want to do all your extractions. So you can see that we can do a boxcar extract, and we're going to extract the spectrum width. Okay, boom. And here's our extracted spectrum using SpecReduce. And we can plot that up, and there you go. Okay, so far so good. The next thing that we're going to do is define all of our weights, okay, so that we can do an optimal weighted extraction, and we do that. And we're able to show that here's the boxcar weights, and here is the pipeline file. The pipeline file does have a different calibration. That's because the way this pipeline file was produced was in the old days when the pipeline wasn't fully calibrated. It is calibrated now, so that should match if you do it with your more modern set of data. But when we created this notebook a while ago, it was not. You can also do PSF weighted extraction, where you're weighting based off of the PSF. And we can take our high signal to noise spectrum and create a weighted file. You can see the highest weights are in the center of the trace. Here's what that weight looks like as a function of wavelength as you go down the spectrum. And then you're able to do also an optimal extract, where you have your trace, but also a weighted array. Okay, and so we call that extract 1D PSF weight. Okay, and we are able to convert that into flux units and compare. And you can see, because this was a high signal to noise extraction, the boxcar with the background subtraction and the PSF weighted optimal extraction are all relatively similar. Okay, So then, yes, again, you can plot up all the different spectra if you want to put them into SpecViz just for fun. And you can also do a comparison with Matplotlib.